for today's class, so we are basically from today's class, we are moving forward with models and deployments overall. Okay, so like how to basically, you already have some models developed, but then how to optimize those models, how to deploy those models, and where to deploy those. So this becomes this class and upcoming basically series that are coming. The first thing that we are going to talk about is called Neural Architect Search, or NAS. Okay, and before we go to neural architect search, we basically start with hyperparameter tuning. And so if you, this doesn't, no, sorry. Let's start here. Now, so what is NAS? So it's a technique for automating the design of neural networks. It's technically part of something called AutoML. Okay, so it's like there's a field AutoML, which the idea is that how can we automate this model development process? Within that field, there is a subfield basically called NAS, which is focusing on automation of the creation of neural network. Okay, neural network architects. Now, screen reverse. So first, now that we're going to talk about the hyperparameters, hopefully you all know that there are two types of parameters when it comes to models: parameters and hyperparameters. So parameters basically is anything that the model technically learns. You know, during the training you learn and update. Hyperparameters becomes anything that you set before the training. You decide on those values. The trainable parameters like parameters, they are straightforward because you design it and the optimization algorithm that you pick will learn that for you. So you are not technically responsible for manually learn those. But the hyperparameters, you're responsible for those. And we all know that, especially for algorithms, the types of models like neural network, that hyperparameter that you select could easily put you in a local minimum. Right? So it has a really huge impact on the outcome that you will get. Now, the idea here is that how could we select those hyperparameters? You know, and probably lots of you have done that manually. I have done it before also manually. Like you just select and you have this table of it. I selected this was the score, and this, and so like that. And that's not feasible. Why? Because the larger this search space that you have is, it becomes impractical for you to manually try to set those. Now, the idea will be that how could we automate this process that we basically don't need to manually do that. Now, when we talk about hyperparameters, hyperparameters could be your architect choice, activation functions, weight initialization strategies, or just optimization parameters like learning rate and stuff like that. So those are like all hyperparameters that you need to basically select. One of the really good libraries for that, if you're a TensorFlow user, is called CrossTuner. Yes, if you want to develop basically neural network models, it's really good for hyperparameter tuning. PyTorch has its own also. I think it's called PyTorch Search or PyTorch Tuner, something like that also. Scikit-learn has its own. All these libraries, they have these hyperparameter tuners, basically. Now, if you, I'm not going to go over the lab, but just going to show you how this CrossTuner works. So think about you have a model, you're building a model like this, and all of these values that you see here from activation functions, this number of nodes, dropout values, I don't know, like the loss or the learning rate, all of those are decisions that you make. Okay, so these are basically you decide. Now, in order to automate this process, instead of manually decide on those, what you can do is use something called CrossTuner, something like this, basically. So think about the dense layer, the simple dense layer in TensorFlow or Keras. Basically, you do model add, and you put this dense layer. And here there is a unit, which was the hyperparameter. You decide how many units you want to pass. So instead of manually pass that with CrossTuner, you create a function. This HP unit is a function, you say that it's going to be integer because it's number of nodes, it's going to be integer. The minimum value is 16, maximum value is this, and the step size is kind of like a for loop technically, right? And instead of putting the actual number here, you put that function here as part of your layers, basically, in your model. And so on. So you basically, anywhere in your code that you want to do some sort of like a hyperparameter search, you use this technique. All starts the same thing. So you build a function, HB stands for hyperparameter. And if you search on their website, it has integer, float, basically. So it has all sorts of numerical. It has for categorical, it has for Booleans. So basically, it just adds this function for you that you can add to your model. One thing that you want to keep in mind here is that the larger the number of search that you add, because think about it, if I add only one hyperparameter, which is this HP, I have one dimension that I want the cross to search for me. It's only for this parameter, HP units. But as soon as you go to 2 dimension, now you have a second search. So if you only have 1 dimension, this is going to be the search space, right? You search along this, starting from 16 to 512, right? Now, as soon as you go 2 dimension, this becomes a square. If you go 3 dimension, basically, this becomes like a cube, right? This becomes a cube. And imagine, as you go higher, this becomes more challenging. So even despite the fact that these tools like cross tuners, they are pretty good for these types of things, one thing that you want to keep in mind is that don't add it for everything. Why? Because despite the fact that it does all the search for you, it's still going to be a slow process, okay? So you want to be sure that you add this hyperparameter for parts of your model or layers that you know actually it's important for you to find an optimal value. Some of the values, maybe you don't need to find optimal. Maybe, I don't know, if you're dealing with a dropout, maybe you just have a fixed dropout. You don't need to let it search from 0 to 1, find the dropouts. Only basically add those for the parts that you think is more important, because again, otherwise the search space is large. Now, the next thing, basically you first build your model layers by adding this hyperparameter tuner. And then basically the way that you basically started, cross tuner.hyperband. So hyperband is one of the algorithms that we have. We're going to talk about today about different search algorithms that you can use for this type of things. Hyperband is one of those. You pass your function and you say, what is the objective function that I have? So I'm interested in increasing the validation accuracy. So you say validation accuracy, what's the maximum number of epoch you want to search for one iteration? That means if I pick this point on the space, which gives me a hyperparameter, okay? How many epochs do you want to let the neural network to train over this data, over this hyperparameter? That's that max epochs. That's really important, because if you think about it, if you have 1,000, for example, point that you want to search over, each one of those 10 epochs, that becomes 10,000 epochs, right? So you need to basically keep in mind all of that when you want to decide what's this max epoch. Factor, just leave it 3. There's a directory where it says to, there's a project name, leave it to be. Now, overall, so hyperband is one of them. The other one is random search you can use, Bayesian optimization, and sklearn also is one. So these are 4 types of search algorithm it allows you to use. You have seen the hyperband before. We talked about it, but we will see it before. Remember that band that you basically pull up? We had this example of, but we'll get there if you don't remember it. So you basically let that, you basically create this tuner, and then you basically define some sort of like early stopping. Basically, you say to monitor the validation loss, and if it didn't improve by 5 epochs, then stop. Then you start the training like this, tuner.search. You pass the data. Total epochs is going to be like 50. Validation is split this, and you put this callback, which is that your earliest stop, and you let it to run. When you do this with Keras Tuner, it starts to basically run something like this, and it gives you this result. So it basically tells you that what's the trial number, and this part, it shows so far which iteration has the best result, and what are the hyperparameters, and what is the current one. So you basically search through all of those. What it does, it will give you this UID for metadata. It creates a metadata on your machine, similar to metadata that you have seen before. So you have access to, you have this protobuf data basically that you can access through those. But it's pretty good. I highly recommend you basically to start using it if you are doing a model development with TensorFlow. And even if you are not doing TensorFlow, if you're doing PyTorch, if you are doing scikit-learn, or any of these libraries that they give you hyperparameter tuning, don't do that manually anymore. Just use these techniques, because the result that you will get with these hyperparameter tunings are much better the values that you're going to manually come up with, right? And much faster, because you just let it run maybe for a day, depending on the size of your model, for example, and you have the result of all possible searches, and it gives you which one is the best. Now, we will talk about this, but how this model decide which hyperparameter is the best if it only goes, for example, for 10 epochs. So the one thing that they do is kind of some sort of like an interpolation. So that means if this is, for example, if this is epochs, and this is, let's say, F1 squared. Okay, so starting a search, for example, it goes like this, and then it stops here. And there's another search you will see, for example, goes here, maybe it stops here, and so on. What happens technically, it goes maybe to 5 epochs or 10 epochs. From here, based on the trajectory of move, it interpolates where it will be in 20 epochs. Okay, it's kind of like interpolation, that or where it could be. The one that you normally it selects as the top, it also tells you that some estimate is going to be here, for example, in 20 epochs. So it's kind of like an interpolation of where it thinks it will go based on how it trained within that 5 to 10 epochs, for example. So that's basically how they work in the background. Any question on that? Yes. Will it what? If you're asking that, will it saturate during one epoch or during between epochs?
After the point, after taking some.
Okay, so it's possible. And the thing is that it's possible that you go to some point and after this, it's kind of like a saturation. But I think the way that when we do interpolation, the way that we are looking at the movement trajectory, you kind of have some like identification of if it's going to saturate. You kind of guess that if you basically see something is going up so fast, then you all of a sudden see there's a drop down, or it's going to slow down, then you can estimate that, yeah, it might saturate. So I think it has something like that. So it's the final that gives you, it doesn't technically saturate. But also one thing to keep in mind is that these are neural network. The final answer that it gives you doesn't mean that it will give you the global optimal. It's still going to be a local optimal, but maybe it's as good as, it's the best scenario for you rather than manually basically going through those. Now, so next, that was a hyperparameter tuning. We're going to now go on AutoML. So we're going to talk about AutoML, or we talked about NAS, but we're going to basically go deep in the NAS concept. We're going to talk about search space, search strategies, performance estimation, and we are not going to go AutoML on the cloud, that one. So now, AutoML, or automated machine learning, the idea was that, okay, could we basically have some sort of pipeline that iterates over different models, model architects, and basically come up with its own machine learning model or neural network basically model. So it doesn't mean that it doesn't need an engineer in the loop. You still need to build this pipeline or to put this together, but for certain things, you don't need to manually maybe build those models. It's a pretty new, not taking new, but it's pretty evolving field. So that's why you haven't maybe heard of it much. It's kind of like evolving. But on the cloud, certain providers, they have that, like on GCP, Azure, on AWS, they have this service that you can basically use. Now, so let's start with here. So neural architect search. So they are, when we talk about NAS, again, the focus is that how to build neural networks without manually creating those. And what does manually means? When you want to build a neural network classification regression, you decide, I'm going to add this layer, this layer, this layer, and so on, right? So how do you come up with those layers? It's kind of like either domain knowledge, or you do some search, or kind of some sort of like a random, you just stack them after each other. Now, if you want to build larger models, stronger models, are you actually manually going to come up with those, or you have some strategies? So that becomes the idea here, like how could we come up with some strategic way to build these neural networks? Now, when you work with NAS, there are three concepts that you want to learn. First one is going to be search space. Search space is all possible architects or layers that you are allowing this algorithm to pick from. So imagine I'm doing, for example, image processing. I don't want the algorithm to go pick some LSTM. So LSTM is not part of my search space. So you still need to come up with a search space of CNN is allowed, I don't know, max pooling is allowed, and so on and so on. So you basically stack the name of these layers that you're allowing the algorithm to pick from. And that itself is one drawback of these techniques. Still, a human need to come up with what is allowed, what's not allowed. Okay, so it's kind of like there's some bias basically of selection in the technique. After that, you need a search strategy. Search strategy is that, okay, I have this search space. Now I need to be able to go and pick the one that's useful from that. And every time you pick something, then you need to have a way to evaluate it to see if it was a good decision or not. So after search space, you need a performance estimation strategy. So it becomes three main parts: the search space, search strategy, performance estimation. And this is basically the one I see on top is the algorithm that you created. So search strategy picks something from here. You have a builder. The builder puts it together, pass it to this estimation. It basically it goes through a couple of epoch, basically kind of like interpolates where it's going to be in the future, gives a feedback to the search space, and the search strategy based on that feedback picks the next layer, or basically reformat or reframe the design. And this loop continues basically. Okay, so now again, this is also like if you think about AutoML, NAS is going to be this part of the AutoML, just for the neural network part. All right, this example we don't need. So let's first focus on the search space. Now, when we talk about search space in NAS, there are two types of search space basically. It's going to be macro and it's going to be micro. Okay, macro is when the design is based on layers. Like you define set of layers and you tell to the model, pick layers from this list, for example. So this is, as we see, this layers, L means layers. So that becomes a macro search space. Then micro, on the other end, you don't provide layers to the algorithm. You actually provide neural networks to the algorithm. What does that mean? So that means there are certain, let's say there are certain neural networks that you know is doing a good classification or doing good feature extraction and so on. So you have worked with those. So instead of giving layers to the model, you actually give the actual neural networks, different neural networks to the model, and you say stack them together how you find is better. That's the idea. So instead of, again, you put layers, you build neural networks, smaller, but maybe they are focused for different tasks and you're aware of that. And you just allow the algorithm to put this together, build a larger neural networks, basically. Okay, so think about, for example, if you want to do an image classification, you want to build a really large model. And you have this idea of, if I put these types of CNNs after each other, this type will focus on colors and edges and stuff like that. So you build that already stacked. because you had this domain knowledge, or someone else has done it and you know it. And then you put a different stack that you want to do certain things about the image. So you build these smaller networks that they're doing a specific task that you are aware of, and you let the model basically to pick from that. An example of that could be, if you think about the concept of the transformers, right? The concept of multi-head or basically multi-layers. So you build a couple of those and you let the model to stack those after each other. You decide how you want to stack them. You know, it's kind of, instead of you deciding how many heads, how many layers for transformers, you just maybe define 1, 2 layers, and then you say that, hey, stack this after each other, or the way that you think is more important. Okay. So that becomes macro versus micro. Now, when we go over macro, there are 2 ways that the algorithms, these types of algorithms, they can design for you. One of them, and this is kind of like have you guys worked with Keras before? You know, when you build models, there are 2 ways you do sequential, functional, right? So this is also same idea. Sequential, that means the algorithm stacks layers one after each other, they fit to each other. Or functional, which the order basically is not the way that it is. This layer could fit to 2 different places and so on. But here also the idea is the same. So if it's a micro or macro, it's going to be either sequential or going to be functional, basically. Then when it goes to micro on the other end, that becomes the idea. So like here, you have this normal cell, basically types of neural network. You have this reduction cell that does a reduction job, or so on. You have different designs of the neural networks, and you tell to the algorithm to stack those after each other based on certain criteria. So at first, maybe the model picks this randomly and stack them on top of each other. It trains it based on the training, and it gets a feedback, and it goes to redo the process and so on. You know, it's just maybe improve the selection. But again, all of these techniques, they have this downside of that you decide what goes to this model. Okay, so it's still at your control. All right, any question on search space? Yes.
Go back to the previous slide, please. For this particular microarchitecture search space, we define architectures as opposed to layers, and it is still doing like a sequential job with stacking, right?
Yeah.
But the cell within it, which is sort of like we're treating it as a layer, the cell within it can have any kind of architecture that we decided to be, not necessarily sequential.
That's correct. So this what's inside this model is your choice. It's so that's not it's not, it doesn't need to be functional. It could be sequential, it could be functional. These are different neural networks. One thing that you want from this neural network is that the input and output for each of these cells technically should be somehow that you can stack on top of each other.
Yeah, so basically in terms of the dimensions of it, it has to be similar. And
that's
so what is the benefit of using something like this?
So, I mean, depending on what you define as a benefit, but think about from design perspective. I want to build a neural network like a large model because I'm trying to build something that's challenging, and I need a lots of stack on top of each other, right? One idea for me is that I just give all these layers to the model and say that you stack them after each other, okay? Which it could work, but the challenge could be that there are some domain knowledge that you have, some contextual knowledge you have about the types of architect that the model doesn't know, the search doesn't know, right? But if you have that knowledge, when you provide this and say that, hey, pick this because I know this does this job. Pick this, I know this does this job, and you let the search algorithm to pick those. Yes.
So let's say we take like 5 layers each. We are making a basic neural network, and we know which layers, like we are deciding which features to use for dropout, for example. Like dynamic dropout, this would allow us to do for those like number of layers, right? Mm-hmm. Something like that.
Yeah. So you use that knowledge that you have, you built these cells, and you say that, so basically use these cells. You kind of like, these cells are not random. It's like a knowledge base, basically.
In that way, it will just give you the right order in which these cells should be present.
That is correct.
Or whether they should be or shouldn't be present.
Yeah. So basically, it's the stacking of this is that this decision on the order or if they should be part of not would be part of your search strategy and the feedback loop that you have. Question? Yes.
Doesn't that mean you go through every permutation you have? Is
So
it
yes,
deterministic?
so these are not going to be a cheap algorithm, cheap techniques. And that's why, again, well, these types of algorithm, the reason are not that common, you don't hear much of them, because they're expensive, right? So Google has it, I don't know, AWS has it, Amazon has it, but you don't hear it, other companies to have it, because, they have it because it requires a really good compute behind it in order to be able to do this. So they offer it as a service, but yes, it's going to be expensive. We're going to talk about that search strategy right now, how maybe we can make it cheaper. So, that actually goes to the segue that search strategy. Now here the idea will be that, well, should we go through all of this combination, or should we just be more smart in the searching? So there's a couple of techniques that basically we can use, like grid search, random search, Bayes optimization, evolutionary algorithms, or reinforcement learning. These are the types of technique that are being used in order to basically do this search, to basically, the first two, which the name is obvious, grid search and random search, kind of like they're like one of them, the grid search is like exhaustive, you just go through everything. And the other one is random search, but random search is kind of like a greedy algorithm. So you just basically keep randomly going through everything, it's kind of like one of them has the order, the other one doesn't have the order. The problem with these two techniques is that as soon as the search space increases, they will basically fall back. Okay, it's kind of like, so for a small search space, yes, they will work, but for larger search space, they basically won't work, these techniques. They're pretty slow, or they won't even find something good for you. Now, the other one is Bayesian optimization, which is pretty popular. You also see it as part of scikit-learn, basically, or Keras-Tuner or scikit, they all have this Bayesian optimization. The idea behind the Bayesian optimization is that we basically say that the model's performance comes from basically Gaussian distribution. Okay, so basically, let's say this is the F1 score, right? This model performance. What we are saying that, well, there is this Gaussian curve, okay, that the model performance could come from here, right? Depending on whatever hyperparameter you select or whatever architect you select, we can predict or we can basically find that PDF. What is the probability density function for this hyperparameter, for the performance given this hyperparameter? That means what is the probability of F1 score being something given this set of parameters or this architect design? And that comes from a Gaussian. So lots of time is low. Sorry, a small amount of time is low. Lots of time is in the common range of F1 score. And there's a rare scenarios that you could get the highest F1 score, right? So this type of technique basically, in order to decide if the hyperparameter or architect is good, it basically has that the PDF. Use that PDF, it makes a prediction that yes, it's going to be good or not, or it's going to be bad, basically. So that becomes the Bayesian optimization. The other one is evolutionary methods. And this one is kind of like, if you think about what we do basically here is that it's kind of like the strategies that you have some design, basically you come up with some called parents architect. So that means at first you have certain architects or certain nodes, and you say that, well, these are the one that you can select from. Then you have this algorithm that's kind of like a selection algorithm, like a sampling algorithm, or it goes over this parents and decide, and that's a hyperparameter itself. You decide top two from that parents. How do you do that? Let's say, for example, I have 10 parents. I actually I have 10 parents, and each parent is a neural network, a small neural network, right? I pass the data through each 10 and compare them to see which top two gives me the best result over the same data. So you pick the top two selected parents. Then the idea here is that you want to build offspring from those parents. So you combine them, you basically create a new architect from the top two parents. So top two basically tells you that, for example, top two is a number. Basically tells you that this architect was doing better than the other architects that we have. So you say, okay, I know these architects are good. I'm going to add some couple of things to this architect, do some addition, and I'm going to use that as a child, basically. So you introduce here 3 new architects or neurals, basically node. Then you go back to the original pool of parents that you have. You get rid of the worst 3, the bottom 3, basically, and you replace this top 3, the new 3 in that pool, basically. So now you have this one, and this loop continues. So the idea will be that you constantly changing this architect by figuring out which one is the good and doing some basically change in the genome of that parents and basically improving it. Right? It's kind of like there's it's called evolutionary method. It's kind of like the idea of like a change in evolution, right? It's kind of like a changing in improving basically the genome of the models. That's the idea. And you let this loop go through until you basically meet that certain whatever convergence criteria that you have. Any question on that? Yes.
Is there like some sort of optimization function or survival scope you need for that? Because you need to prove the agents that are not correct, right? So how do you determine if your agent is?
The next slide. No. All right, so these are basically, so this is, let's go actually after the reinforcement learning. So far we're just talking about the search strategies, how we can build this together, right? So the next one, reinforcement learning, which I don't know if you have taken the course or something before, but the idea will be that if you have an agent and there is a search space and how the agent could basically goes through this search space, basically takes the best action. So the idea of reinforcement learning is that it's unsupervised, right? So you have an environment and you don't have a data, but in order to basically learn from the environment, you take action, and each action that you take has some result. And that result is either as a good reward or a negative reward, basically. It's like either positive or negative. And based on that, you learn next time, should I do this or not? It's like there are much more to it, like, but overall, now think about it from the perspective of creating these neural networks. You have an agent that you give this all the search space and it makes a decision based on some policy. So in order to make that decision, what the agent should do, you have something called a policy. And policy is the one that you update. Your goal is to optimize that policy. Policy is basically mapping your current state to an action. That means if right now I'm standing here, what's the best action should I take? At first, you don't know, it's random. You just like, you take all sorts of actions. But as time goes and you learn this feedback, then you have this idea of like, when I'm here in front of the class, at this moment is the best action for me is to do this. That gives me the best result maybe right now and overall through the end of the class. So that's the idea for the agents in the reinforcement learning, to learn a really good policy which maps you to the actions, maps the states to the action that you basically want to. If you optimal the policy, basically you optimal the policy with the goal of optimizing the overall long-term reward, okay? So that becomes the idea here. For the search of the architects, it also becomes the same idea. Questions? All right. So now this example of NAS, basically they use reinforcement learning. I think the paper is also on the class channel. But so the idea here was that it's actually a really interesting idea. So think about you want to build neural networks. And one idea was that you have all these layers and basically searches, like the architects of model that you let search through this. What they did in this paper is that they built this like a text generation. You have a model like a GPT, for example. It's before GPT, but think about like a GPT. It generates text, and you ask this model, "Hey, I want like think about that." You ask GPT and says, "Write a poem for me," right? And now imagine you ask this model and it says that, "Give me a neural network with 10 layers," and it generates a text for you. That text describes this neural network in a textual, basically, form. There's a neural network with first layer is this, has this many parameters, and so on and so on, right? So then you pick this text and you pass it to some sort of like a builder, converts the text into layers, basically. You have a mapping. This means this layer and so on. You parse it out into a model. So you build a model over that. You train the model. You see how good it was. You do back propagation to update the text generation model. So the result that you get from the cost function, you use it as a back propagation to update this text generation GPT model, for example, that you have. So your goal is to update this. If this model gets better at generating a text that yield a higher performance neural network, that's a strategy that you have. That's what you want, basically. So you generate text, train a model on that text, compare, see how good it was, feed it back to the controller, basically, that you have to generate text again and look through it. Does that make sense? Okay, so yeah, so that's one. All right, now let's go back to what your friend asked. Okay, how do we measure this? How do we decide that if this is good or bad? Well, there are a couple of ways that you can do that. One of them, for example, it could be validation accuracy. Like you have this fixed data that you compare against it as you go through them. The problem with validation accuracy, despite the fact it's really common, is that, well, it's computationally heavy. It requires GPU, TPUs, and stuff like that, and it's expensive overall. Why? Because if you think about, let's say you have this validation accuracy, like 5 million records you go over every time. So every time, or 1 million records, every time you create an architect, like a design, the model needs to test it against like 1 million records, and then goes to the next iteration and continue that. So that becomes really expensive for this type of algorithm, search algorithm, every time you want to test it against a validation data. Now, there are a couple of techniques that you can use for reducing this costs, okay? One of them is called lower fidelity estimate. The other one is learning curve extrapolation, which is same thing that Keras does over there, Keras Tuner, this one. And the other one is weight inherent or network morphism, okay? And I'm going to go over this one. So lower fidelity estimate. So lower fidelity estimate, the idea behind it is that, well, instead of using, for example, think about you have an image and you want to test your model. Instead of using the high resolution image, you reduce the resolution, lower fidelity, and then you test it against that. Instead of, for example, I don't know if you have lots of filters, maybe only apply a certain number of filters to the data. If you have a data set, instead of you doing across all of it, you do subsets and just get lower fidelity. That's the whole idea. But it only works if at least the first time when they talk about it was that if the relative ranking of the data by doing this lower fidelity doesn't break. However, there are some research recently that they say that that's not the case anymore. So it doesn't matter if it breaks the relative ranking of the data, this technique, this approach, it still works. Okay, so that's one way of reducing the cost. Technically, reduce the resolution of your data, reduce the dimension of your data, and then do the testing, basically. The next one is the learning curve extrapolation, which is exactly back to what we were talking about. So it's kind of like you go a couple of epochs, you have some idea where it's going to be maybe after 10 epochs, after 20 epochs. And based on that, you decide which one is going to be the top runner. Well, of course, this itself requires you to have an extrapolation algorithm right? You need to have some sort of, I don't know, maybe a regression model that's really good. Given 5 epochs, it can predict exactly where you're going to be in 20 epochs, right? So that's because that can highly impact, the decision that you make. If your algorithm is not good, then your result is going to be bad. So this is going to be learning curve extrapolation. And the next one is weight inheritance, or basically network morphism. So network morphism, we're going to talk about this more. And these days, actually, the idea of this network morphism, or it's really similar to distillation. It has become really popular. So, for example, if you think about the DeepSeek, so what basically they did, the building that distilled model, the smaller models, that's the similar idea here. Okay, it's kind of like so the idea is that I have these larger models. How could I basically transfer the knowledge of those large models into much smaller models? Okay, so the network morphism, basically, the definition of morphism is anytime you change from a function to another function, but the nature of these two functions should be the same. So that means that if it's a classification, you go to classification maybe, right? So the nature of the function should be, if it's additive, you go to additive, you don't go to subtraction. It's kind of like that's the idea of morphism. But you basically have this called parent model, a large model or a base model that you have trained before, and you want to transfer the knowledge of that very large model into much smaller models. Okay? So the benefit of that is that the cost, the computational cost for the new model that you build, the morphism model that you have, is much lower than the cost of the base model. So if you train the base model in 10 days of GPU works, multiple GPUs, maybe the morphism one, it just takes 1 day of GPU works. Okay, so that's the idea. And then the network size is not bounded also. Any question on that? We will have more on this morphism as it comes. Okay, so I don't want to go on the cloud concept here, so just continue from here. So that was just we talked about the model designs and how you can automate some of these models design, especially for neural network and when you want to build the larger models. So the next thing we want to talk about is, okay, let's say I'm building these models, and what about the resource constraints these models have? That becomes more important, because if you build a model, if you have a really good search technique also, and you build a model but you cannot serve it because it's really costly, then it's not useful, right? So now the first thing we're going to talk about going to be dimensional reduction and different types of dimensional reduction and why they're important for the performance of the models. So think about what we had before. Was the idea was that, well, this back in the days, the idea was that really be careful in selecting features. So you basically build all these features like from domain expert and stuff like that, feature engineering. But now basically we have lots of compute, we have lots of storage. So these days we don't care much about those types of things. But one thing that still we care about is to squeeze the most out of the data, right? So, and then also we need to be sure that, we know the challenges that high dimensional data have. So one of this thing, a good note about neural network is that how often have you heard this term? I don't do feature engineering, give it to neural network, it will basically figure it out itself, right? It's common, right? It's true, it does. It actually maybe doesn't need the feature engineering, it basically take care of it for you. But that's not free. When we say that's not free means that if you have a simple neural network, like something like this, right? And you let this to learn all the features. What happens here is that if later you go back on the trained model and look at the features, you will find, or the nodes, you will find maybe certain nodes are technically don't do anything. They're just denoising for you. They get like data goes through them, maybe the weight is really almost zero. right? So what happens basically is that you feed all the data to the neural network, but the neural network need to learn how to discard them, technically. So good portion of your model actually has gone for nothing. So you have this model, which technically, if you think about from the cost of neural networks are not small, they're normally large. They are heavy. That means even if you compress them, depending on the size of the model, some could be in gigabytes. Like if you download these days any of these models online, Llama and stuff like that, like 8 gigabyte, 10 gigabytes, right? So neural networks are not basically light, they're heavy for the size perspective. The larger the models, also despite the fact that not just the disk space, is going to be the slower the model from the compute perspective. Now, if you have these nodes that they just learn to do nothing, you know, you pay the cost for the storage, you also pay the cost for compute through it, which does nothing, right? So it basically makes the problem worse for you from the deployment perspective or from serving perspective. So the idea will be that, well, could we improve that rather than we just feeding it all to neural network and says that, hey, you figure it out yourself. Let us help that. Let's basically do something about data and ensure that the model basically receives the good data. So think about the example of like a word embedding, for example. So we have data before word embedding was kind of like a one-hot encoding. And we saw that, well, it's pretty challenging. So what did we do? We basically converted from higher dimension of like a one-hot encoding maybe into basically a word embedding, where each dimension on that word embedding has its own meaning, basically, right? So that's the idea of the embedding layers. And the embedding layers itself, it's a huge search space or huge space, basically, if you think about it. Now, let's look at just one example here. So think there's just one number we want to change on this. So here, number of word 1,000. So 1,000 here. So look at the difference here. So here we have number of word. Basically, sorry, embedding dimension is going to be 1,000. Or number of words for embedding dimension. This is also 1,000. So 1,000, 1,000. Sorry. So we have both number of words 1,000, and we have embedding size also basically 1,000. And this is basically the result that you get. Now, if you change it to 6, you know, and this is the result that you get, right? So it's kind of like, it has a better validation in compared to the other one, right? From 1,000 dimension versus just 6 dimension. It's kind of like lots of that space that you design for the embedding is technically do nothing here for your model. Now, all of this basically comes back to one basically common problem that all these models have, and this curse of dimensionalities, right? So we all know that the curse of dimensionality, it's, we think about this simple example of if I have 2 columns, X1, X2, and I'm doing a classification, and let's say X1 and X2, they are binary. So I have 1, 1, 1, 0, 0, 1, 0, 0. That's the maximum combination, right? So that means, let's say this is 1, 0, 0. In order to learn this classification, I only need 4 data points, right? I see all the combination, basically. Now, what happens if I add 1 new column, X3, and it's also binary? Now, how many data points you need? 8, right? So it's quadratic increase just by adding 1 new dimension. So now think about it, that's where the curse of dimensionality comes, because you added 1 field, 1 column, but you need twice more, basically, data points. Now, every time you add dimension, think about how many data you need in order to be able to learn all the combinations. And that's where why it yields to basically curse of dimensionality, because you end up with not having all those data. Like you don't have enough data for that. Now, lots of machine learning models, basically, they are distance-based, like from k-nearest neighbor, support vector recommendation system, and they all have some sort of distance functions that we are using. A common one is Euclidean distance, right? So anyone knows what's the problem with distance or Euclidean distance, for example, and a higher dimension?
And it is just a linear line, right? So if you, even if you include multiple like dimensions in that, it can't capture non-linearity that.
Not about nonlinearity. So the question here is that, so this is a Euclidean distance, right? If you increase k, this n, what do you think is the problem? What could be the problem?
Taking squares and roots. Constant.
Not that also, but at the end is a number, right? So you can basically calculate the square root. What else?
Oh, every permutation you have to do. Like you have to, like you're taking two at a time and you're doing minusing for that. You'll have to.
Let's say the time is fine. Let's say you don't care about the time. What could be the problem from model learning perspective?
What is more important if you do dimensionality reduction? Like the distances between two features, one could be, let's say, demand, right? Demand is like really high values for those. And then you're checking that against something with, let's say, very small features, like 5, 6, digits, regular digits. And that becomes really a big difference. And then you don't know which one to prioritize. No?
No.
I'm assuming the data is regularized.
Let's say data is regularized, yeah.
Differentiating the groups.
The more dimension you have, the larger the Euclidean distance. That's the square root, right?
Yeah.
That doesn't matter what's the value. If the more dimension you have, the larger the distance.
Right.
So you get to the point, if you have too much dimension, points are far from each other. Doesn't matter how close in reality they are, they're going to be so far from each other. So if you're doing an algorithm which is a distance-based, all points that you have are far from each other. As soon as the dimension basically increases. And we can see that. So let's first talk about this. So more dimension, more features, risk of overfitting increases. Distance grows more and more. No clear distinction between cluster object. And this is what they call concentration phenomenon for Euclidean distance. It loses that concentration. It's basically the distance are so far. Now, first let's look at this example, then we come back here. So on the left, you have only one dimension. That's the data. As you go to dimension, 2 dimension, this is the data. And if you go to 3 dimension, that's the region. You see the points that are so close to each other, the more dimension you have, they become so far apart from each other. And that's the problem, which is something that for you to keep in mind, if you're working with distance-based functions, maybe having more dimension is not good because it becomes hard for these types of model. Even if you do clustering, they're going to be so far from each other. So that's why the dimensional reduction becomes important.
But we do PCA first and then apply.
But that becomes dimensional reduction, right? Becomes important for this type of things. Now, okay, why more features are bad? Well, more features means redundancy, irrelevant features, more noise basically. It becomes hard to interpret or even visualize the data. And even it becomes harder to process and store the data. Even let's say you have done all of this. For serving, you always rather to have a small number of features that you need to pre-compute for making a prediction for a user than a large basically set of features. So that makes it slower. But the overall basically, there is some sort of basically detection that you can see that there's always some optimal dimensionality. That your model performance increased by then. After that, it will go down, right? So it's really important for you, maybe as part of that EDA that you do, feature selection that you do, to figure out what's that optimal value for you. It's that's why we have seen the other algorithm. We did have a lab on this different feature selection that we talked about, right? So you can basically let that run on your data, figure out what's the optimal number of features for you and just use that. All right. So this goes back to the same thing that we just talked here, 1D versus 2D. And then again, that's the curse of dimensionality and distance space, because again, this is not negative sum, it always will increase. Okay, so Now, there is a concept called Hughes effect. So Hughes effect basically says that the more feature, the larger the hypothesis space. Doesn't matter what's the algorithm. So irrespective of the algorithm that you're, or types of model that you're designing, the more feature you have, the larger the hyperspace, and then basically the slower the model gets, or the harder for the models get to converge or to learn, basically. So now, let's go over the, sorry. So let's go over this dimensional reduction and basically overall, basically how it can help. So the first thing that dimensional reduction can help is the runtime and system memory that it requires. It's when you want to run the model, the larger the basically number of dimensions, the slower that it gets, the more memory you need to feed it basically in. It's normally takes longer to reach to some sort of like a global optima if you reach to any. And basically, more features that you have, the higher the correlation basically among the features. So you have a higher chance of multicollinearity basically. Now, so more features doesn't mean they get a better predictive performance. It's only, more features is only good if they actually have some predictive signals, right? And we also talked about it, it will increase the number of dimensions or the data point that you need and basically reduce the model usefulness. A simple example here is that imagine you're building a model like this, that you have these features that you're feeding into this model. It doesn't matter what's in it, but, and then now you're adding one new field. So here on top, we just added one new dimension to this model. We want to see the comparison between these two. So the first model has 833 parameters that need to learn. The second model has 1,057 parameters that you need to learn. And you just added one dimension to that. So think about that when you build these types of model, when you add just one features or one dimension, how much impact it will have overall on the cost of these models. Now, okay, so there is no rule of thumb to figure out how many features do I need, right? It's kind of like something like a try and error or optimization for you. Number of features basically all depends on variety of things, what you are trying to do, or what type of algorithm you are using. Now, if you want to reduce the dimensions, well, the first easiest thing is that manual dimensionality reduction, right? So you just basically, you have done it before. You could basically reduce the number of dimensions that you are using and decide what's the best combination to use. For example, you have some initial features and then you combine those and basically you do some, you apply something manually that basically like correlation analysis or something like that, and you decide I'm going to get rid of these features and keep this one. That becomes the manual. We have done it probably before. The benefit of that is you get the storage, computation, consistency, visualizations, better engineering, you do some sort of like a selection. So all of this has improvement that the dimensional reduction requires. I'm not going to go over feature engineering. I assume they all have done this type of things. But, and this one, I'm just passing the cross, sorry. It's labs, you have those. So let's go here. Now, what about algorithmic dimensional reduction? Instead of manual dimensional reduction, let's look at the algorithmic version of that. So the first technique is going to be linear dimensional reduction. Okay, so it's the linear dimensional reduction is the types of models that basically you project features on a basically linear dimension. So it's kind of linearly projected. PCA is one of those, for example. If you think about in PCA, every basically principal component that you create is, so if I have, this is my original data, X1 and X2, and this is the data, and you build one principal component, you map this point onto one dimension, and how you technically have some sort of like a W1 X1 plus W2 X2, linear projection per principal component. So that's the idea. So the goal of this type of techniques is that to reduce basically the number of dimension that you have. So you map the data from high dimension projection into a linear basically space. Now, when it comes to k-dimensional subspace, depending on again the techniques or the task, the downstream task that you have, if you're doing a classification, well, your goal is that to maximize the separation among classes, right? So LDA or linear discriminant analysis is a good technique for something like that. If you do regression, the goal is that in the regression, you want this line somehow there's be higher correlation among points, right? So over there, you can do PLS, like partial basically technique. And if you are doing something like an unsupervised, well, your goal is that, for example, in PCA to maximize the projection variance or minimize the projection distance, right? So that becomes a good technique that you use. So depending on what you are trying to do is a classification, regression, unsupervised, you can decide on the technique, the algorithm that you want to use. So let's just start with PCA. I know you all have done PCA, you're really good at it. One question, what is the main challenge with PCA?
We cannot use the original columns, like we cannot represent PCA1 as the original column. How much impact the original column has on the.
So interpretation. Okay, what else? That's correct. What else?
We're changing the original inputs.
What was that?
We're changing the original inputs by accelerating.
So actually PCA, if you think about it, after transformation, the shape of the data remains the same in PCA. It's the way the projection that's kind of work is that in PCA, you technically centralize the data and you apply some transformation. So the shape of the data will change, only the axis becomes kind of like a thing. But the rotation, the axes are basically perpendicular. What else?
I think it's based on eigenvalues and eigenvectors, and you should be able to calculate those in the first place.
It's so PCA is yes, so that's correct. It's based on eigenvalue, eigenvector of the covariance matrix, basically.
So it does not always exist.
Well, the covariance matrix exists. You basically can calculate the covariance matrix if you have a matrix, right? So x minus mean times x minus mean. So if you can calculate the mean, you can get the covariance of that. So that's not a challenge. So it decorrelates the data. That's correct, but that's the goal of it. That's not the challenge. What else? If you pick at two principal components, principal component 1 and principal component 2, okay? So let's say PC1 versus PC2 or versus PC3.
One is hyper selected, like one of them has way more importance than the others. That's why it's called principal.
Yeah, so in PCA, the components that you get are not fair. So the game is not a fair game. Why? What does that mean? You first find the first principal component. First principal component is a principal component that has the highest amount of information. And let's say this is first principal component. Now for selecting the second principal component, I don't have any option except perpendicular. I only can put one perpendicular to it, and then third one, and so on and so on. So as you go through these dimensions, as you add principal component, the importance becomes less and less and less because they're kind of forced to sit somewhere, right? So that's actually one of the biggest problems that PC has. It's like it's kind of like you enforce it to have bad, basically PCAs or principal components. Okay, so I'm going to pass from PCA now. Don't need to go with the algorithm. All right. Now, we're going to talk about other dimensional reduction technique outside of the PCA. So for the unsupervised, so we have latent semantic indexing or analysis, LSA or LSI and LSA, which are SVDs, support basically singular value decomposition based. There's a lot more you use them in NLP. If you have, for example, a document and you try to basically reduce the dimension of these documents or basically based on the data of like a document categorization, basically. Think about something like that. Then we have ICA, independent component analysis, which we're going to talk about, is similar to PCA, but has improvement over PCAs. Then we have non-negative matrix factorization, and then we have latent direct allocation or LDA also. Okay. So, well, the first two basically start with the singular value decomposition, which the idea basically in SVD is that, well, you have a matrix and you want to decompose it into its constituent basically parts that, if you think about, for example, you're doing a recommendation system, and then you have a table of your users, and these are like the name of the movies, and if they give a rating to the movie, or if they watch the movie, how often, how long they watched it, or something like that. Maybe you have a table like that. And let's say you have this, and your goal is that, well, now I have this new user 0. I don't know anything about this user. It just comes to my network, and which movie should I recommend to this user, right? So you have this large table of current user, all the movies. You want to know that how could you apply this knowledge to this user that you haven't seen before? You know, so think about if you go, for example, on any streaming platform, first time you go, there are some recommendation without even knowing anything about you. Where do they get that information? So one technique here, you could do SVD, or singular value decomposition, which the idea is that if you have a matrix A, you can decompose it into something like that, 3 matrices, right? Left singular, right singular, and singular value matrices. Now, the idea here basically will be that, well, you create 3 matrices. Now, the size of this 3 matrix, actually, it varies depending on the types of SVD you use. There are types of SVD that this 2 will be a square. This becomes non-square. There's the types of SVD that this is a square. These 2 are non-square. Because you just want the combination of this multiplication to be this dimension, right? So you have options on that. But the way that in SVD works for this types of task is, if this is a user to movie, and let's say you are this provider, so you have a knowledge. You also have this ranking that you know, let's say there are 3 types of movies: action, romance, and I don't know, like a cartoon. There are 3 types of movie that you serve, okay? So what you basically will do is that the first time, so this is user to movie. What you do, you're going to build 3 new matrices. First one is going to be user to genre. Mapping from user to this genres, basically. And that's SVD provides you. So that means for every user, same dimension. This time you only have 3 dimensions based on the genres. What is the score that user gives to that genre based on overall which types of movie they watched in that genre and how they rate it, basically. So that becomes user to genre. Then you have this third one, the last one, is going to be movie to genre. So how many unique movies you have? So it's kind of like maybe a longer like this. How many unique movies you have and how many genres? So let's say the genre is 3, and here list of all the movies. For every movie, you basically find a score that says that for that genre, how good is this movie? How popular is this movie within that genre, basically? It's some score like that. So you have 2 matrices, user to genre, movie to genre, and the one in the center is like, for example, if here is a square, it's going to be 3 by 3, okay? And it's kind of like a diagonal, basically. It's a diagonal matrix. But what it tells you is that the score of genre itself, how good is a genre? So this becomes a sorted, basically diagonal matrix, and the movie, the genre that has the highest ranking overall will get the highest score, then the second one, and the third one, and so on. So now you have this SVD that you generated over your pool of your current users. Now a new user comes to your environment and you're like, well, I don't know anything about you, but I know what to recommend you. So you go to here among the genres, which one was the top genre? This one. Then you go to this table, for that genre, which are the top movies? Then you pick the top movies. So if you go, for example, to Netflix and you see this ranking comes, Netflix does a different algorithm, but for example, this ranking comes and first one is this bar shows action. There's like a series of action movies in it. So that becomes something like that. And then you go to the second bar and based on the second one and so on. So you basically create them. So as soon as user interacts with that, they select, then you basically try to map the user to users. Now you get, okay, now I know something about you. Now let me see which users that I have are similar to you. So I can refine what I offer to you based on the user that are similar to you and what they liked, basically. So this becomes one type of recommendation system and use like something like SVD. And again, this just some sort of like a, think about it, this SVD is like it reduces that larger dimension of the matrix into 3 smaller dimensions, basically. So the next one is ICA, independent component analysis. So it's similar to the PCA, there's a difference. In PCA, we try to find the directions that reduces this reconstruction error or maximizes the projection variance, like that, depending on how you look at PCA. That's in PCA. And it basically decorrelates the data. So it's like this data are, there's no correlation among these dimensions. In ICA, we actually focusing on not correlation, but on independency among new dimensions. So you want to find 2 dimensions. There's no reason to be perpendicular, but they should be independent of each other, any dimension that you are finding in ICA. So, and also it can address higher order dependency. Higher order dependency means that if you think about from the PCA perspective, PCA look at the correlation between 2 features, X versus Y. X versus Y maybe. But what if you have X and Y given Z, higher order, X and Y and Z given a couple of other features, that's a higher order dependency. These 2 are independent but given something, or these 2 has some dependency because of another field, right? Kind of like if you think about a node, maybe these 2 are independent of each other, but then there is this upper node that this kind of become dependence, or there's a bottom node that these 2 fit to. So it's a higher order of dependency. So ICA can address that, PCA also cannot address that. Okay, so that's another thing. Now, the way that ICA works is that the basically there are two types of parameters that you are learning. There's a matrix A and there is a set of vectors, or basically this independent signals, right? So in principal component, we call them principal component. Here it's called independent signals. There are signals, right? So so basically data, if this is your data, is defined as a matrix times set of signals. Okay, that's the dimension that you're coming up with. How many S could be N if this is D, sorry, if it is D dimension, this could be also D, or it could be less than D, depending on how much you want to reduce the dimension. A is a coefficient matrix, a matrix that only exists there because when you multiply it by this, you want to produce this. Your goal is to find that, but you need a matrix that helps you with that as like a mixing matrix, basically. So, so that's the idea of ICA. Now, in a PCA removes the correlation, ICA also removes the correlation. PCA doesn't address higher order dependence, ICA does. And PCA features are not treated the same. In ICA, they are treated fairly. So it doesn't have that problem that PCA, because it doesn't enforce basically perpendicular. Orthogonality basically is the problem that PCA has that causes this one, right? So it doesn't have that orthogonality either. Now, this is an example of, no, this is NMF. We don't have, we have one. Yeah, we don't have, I thought we have one example on ICA. But overall, just keep in mind, if you try to do PCA, think of ICA, the algorithm already exists. You can basically import it, but test ICA also compared to the PCA. So next one is going to be non-negative matrix factorization, or NMF. So it's a types of dimensional reduction which is interpretable, basically. There is one thing here is that basically it requires the features to be like a non-negative matrix. So it's we don't need to go in details, but it has some requirement basically that you need to satisfy. But if you think about it, this is over the same data. This is the result that we got from PCA. So this kind of like a scary looking images that you see here. But in NMF, you actually can see images. So the decomposition that NMF gives you, it actually blends better features, overall features among the basically face in compared to what PCA does, right? But of course, it's so PCA, this is still nothing, is much lower the value in compared to this one. So PCA is faster, but NMF is much better in compared to PCA here. Any question on those? So those are dimensional reduction techniques, and those are like what you do over the data technically, okay? Now, the next thing here is that, well, what could we do over the model? How could we also apply dimensional reduction or some sort of reduction on the model itself, okay? Now, why do we need to do something like that? So think about my previous company, we were only doing mobile deployment. Like that means whatever model that we would have created, we don't do cloud deployment. It only goes to the edge device, and the edge devices that we were sending the models to, they were like hospital networks, and hospitals. Unfortunately, the machines, computers are really crappy. It's like they have like 6 to 7 to 8 gigabytes of RAM. And really old CPUs and really bad basically management. That's the unfortunate part of the hospital network. So you can't just ship a large model basically there if you wanted to run it on a really small, like a bad computer. And basically, you also need to think about, like, for example, your software is not the only software that exists on that machine. You cannot go hog the memory that machine has. You need to think about it. There are all sorts of other basically tools that, for example, in my case, was being used in a hospital organization or basically hospital network, and clinicians, they use those devices or those softwares. You cannot make the computer slow. You cannot take basically too much time. You need to build a model that's accurate, but also can utilize the lowest amount of basically compute. Somehow that user doesn't notice that this is running in the background, right? So that comes around this idea of like when you deploy to these types of constrained environment, how could you pick a model that you have built it or you're building it, targeting that I want to send it to a small, basically constrained environment, but also ensure that it has a good accuracy, a Font score, for example. So that comes around concept of quantization and pruning. Okay, so short definition is, before we take a break, quantization is you pick the model and you chop the float numbers that it has. All the neural networks, when you train them, if you look at all the weights and parameters you have, they are float 64 or 32. You go and quantize those, basically, bucketize them, all right? And the idea of pruning is that similar to the pruning that you do in random forest, you go over all these nodes and the structure in your network and cut nodes that when the data flows through it, you're like, it doesn't do anything. I just drop it. I don't want it to be there, right? I drop a layer, I drop a node after maybe training, or before training also. We can basically design it like that. All right, let's take a break and then we continue on this one after. So we're going to now focus on this idea of like IoT devices, model quantization. So the idea behind this, like smart devices or the model model deployment is that, well, there always like a good amount of demand these days for this being able to serve models on edge devices. It makes it easier. It's the benefit of edge devices from the compute perspective. You don't pay for it. If you think about it, the user who you basically deploy the model to someone's computer or someone's phone, they pay for the electric, they pay for the compute, everything that you need. You just need to build the model, right? So there are lots of basically interest in it because, well, it's much cheaper if you actually can do edge device basically deployment. It's also compliances with the privacy regulations. What does that mean? No data need to leave the customer's basically environment because you don't need to transfer the data to the cloud to make a prediction. Your model is there, data is there. You just could collect some metadata around how your model performed overall. So, well, it's we also have this online basically model inference basically. Like one question could be that, is it faster if I do it on the cloud or is it faster if I do it basically at the edge? There's something that you keep in mind is that this pre-processing limitation that this, or processing limitation that these edge devices they have. Well, is it faster on device or versus cloud? Think about the communication that you need to do, sending the data to the cloud and coming back. It's definitely much faster on the edge in compared to the cloud, right? Now, but it's faster, that doesn't mean it's really good because if you think about it, the best model, the best mobile these days that you have, I think it has like a 6 to 7 gigabytes of GPU RAM. Like I think the top one probably have something like that. Might be wrong, maybe 8 gigabyte. But not other normal GPU phones, they don't have that much compute. Now, if you build a model, like let's say I build this classification model that I deploy to your cell phone, and you download this app, install this app, and when you install my app, this model goes there and it helps you for whatever task you are doing. Now think about, for example, what Apple has. It has this auto completion algorithms that basically they do the job. Now, if you build a model that it will run on the mobile, but it hogs the GPU on the cell phone, how often you have worked with an app and you feel like your phone is getting hot? Lots of apps they have like that, right? Those are like when they hog this compute resource on the phone, you see your basically battery goes down, your phone gets hot, and your phone gets slow. Every time, if I have an app actually that does that, I uninstall it. I'm like, I don't want it. And most of the users, they do that. So you also need to be sure that, well, despite the fact that I deploy it to the edge device, I need to also be sure that I'm not a hogger over there because easily you can lose the customer or the user that you have. So mobile inference, again, is just the benefit is that, well, you don't need to basically send the information to the data or make a communication. So it has lots of compute capacity, a scalable hardware. Oh, sorry, this is like on the cloud and server, lots of computes. You can deploy all sorts of models basically on the cloud. Well, it's the concept is that it's timely because you need to make the communication. If you think about, for example, self-driving cars, you cannot make a communication to the server. That's why all Teslas, they have a GPU on the, basically you need to be sure that we can render the data, make a prediction quickly over there. Now, when it goes on device, on the other end, the process is that it improves the speed, performance, network connectivity, no end-to-end communication is needed. Well, the concept is that less capacity, tight resource, basic constraints. There are some really good toolkits out there for this edge deployment, ML Core ML, TensorFlow Lite, PyTorch Mobile, or PyTorch Lite or Mobile, one of these two terminals. These are all basically, they have pros and cons. I personally have worked with TensorFlow Lite. I've been pretty happy with it. There's also, Intel has its own OpenVINO. It's kind of like under development, but if you know your customers, they all have Intel hardwares, like especially when you do organizational, like, for example, Northeastern, they all maybe have like an Intel machine, Intel basically chip. Then you basically go and basically change your model using OpenVINOs, for example. That's one of the things that I did before. And then the benefit of that is it makes it much faster even compared to TF Lite, the TensorFlow, because it's built for Intel, if you deploy to Intel and so on. So those are things that keep in mind. These days, actually, we have Onyx, for example. That's another types of basically conversion. Just they'll all be useful. But all of those comes around this concept of quantization. And this quantization becomes we need to have a model. Basically, we want to be sure this model can fit in a smaller constraints, basically, environment. Simple example of quantization is that if you have this image, which is 24 bits, quantization means that if you look at pixels, you bucketize the pixels. Maybe make it from 24, bring it to 8 bits. So when you do that, the quality of the image goes down by default, right? But the question here is that how much I can quantize without losing the meaning, right? So if I'm trying to basically say that if there's any person in the image, maybe I still can go to 8 bits and I still see the person in the image, right? So that's the thing that you keep in mind, like how much you can quantize based on what you are trying to do. Now, why do we quantize neural networks? Because, they have lots of parameters. They take space. They make it slower. And basically, quantization helps you to shrink the model size, reduce the computation, makes the neural networks much faster for inference. Now, this is just an example. So it's for the mobile net. And the yellow or the orange is the float, the general mobile net. The green is 8-bit version of it after you do quantization. So what you can see is that when you reach to, for example, 50% accuracy, you only needed basically what's called runtime milliseconds. So in order to get 50% accuracy, it takes about 6 milliseconds for that model. For this model, it takes about like 15 milliseconds, 20 milliseconds. Right. For the same performance, as you can see, it's like the speed becomes much faster in the quantized version. You can get similar results in compared to basically general version. Now, benefit of quantization is faster compute, lower memory bandwidth, lower power, and basically it supports for basically like a CPU, DSP, NPU, TPU, GPU. So like all of this basically work. And this is overall quantization. Again, it's just simply beating or bucketizing the float numbers that you have. So if you have this float 32, you basically create the bucketize by changing the range to make it also like a shorter. And the idea here is that if you think about from neural networks, when you train neural networks, the reason those weights and parameters have that long, basically number of digits, basically precision, is because we kind of like overfitting to answer for everything. Like it tweaks something by a small value because you want it to not turn left or turn right, kind of like that, right? So those parameters, the precision that they have, the model basically added for a certain reason because you want kind of like overfitting to the data, right? Now the idea here is that, the question here is that, well, does it matter if I cut those digits? What will be the impact of that? Well, the reality is that there will be some impact on the accuracy because the model learned that for a certain reason. But if you have a good model, and that means the model it's not actually overfitted to data. It has learned, but it has precision. Quantization shouldn't drop the performance by a lot. Maybe by a small amount of like by a small percentage, like 1%, 2%. In certain scenarios, we actually see quantization has improved the accuracy of the models because it kind of denoising the channels basically. So now what parts of the model in neural network do we quantize? We quantize the static value, we quantize the dynamic value, and the transformation, that computation, the transformation in the graph that you see, we are quantizing those. Now, There are some, again, trade-off, the model accuracy will drop, and in certain cases, again, that there has been improvement. Now, think about this. This is an example of the model accuracy and model size and latency. So accuracy, latency, size, accuracy. And we want to look at some of these quantized versions. So we have these, for example, Inception. Inception General 1 has accuracy of around 78, and the latency is like a 1.5 seconds to make a prediction. And Inception Basic Quantized almost has 78% accuracy, but it takes about like 600 milliseconds basically. Right, so it's the same model, almost same performance, but it's like quantized version. So always quantization will help. You know, that's the reality. It makes the models faster, makes the models basically better for tight resource basically environment. Now, how do we do quantizations? So there are a couple of ways that you can do quantization. One of the easiest one is called post-training quantization. That means you already have a model, right? You already trained it, it's done. You go post-training, quantize the basically, quantize the floats, the digits, the parameters that you want to quantize. Not, maybe you don't need to do all of those also. You have actually control over which one you want to quantize. So, yeah, so for post-training quantization, there are a couple of techniques that you can apply. Dynamic range quantization is one of those. The benefit is that it makes the model normally 4 times smaller. 2 to 3 times the speed up you get for dynamic quantization. If you do full integer quantization, the model is 4 times smaller, 3 times more speed up you get. If you do float 16 quantization, that means from float 32 or 64 to float 16, 2 times smaller, but it's a GPU support, basically. It supports the GPU. So also that's something to keep in mind. When you do quantization, do a small research to see that will this quantization work for the environment that I'm deploying? If I'm doing a GPU versus TPU, you know, like will it work for those, or is it a good types of quantization? Should I do that or not? But that's something to keep in mind. Now, in order to do quantization, especially post-training quantization with TensorFlow, it's just this. That's quantization. So all you need to do is import TensorFlow. TF-Lite, actually, they have changed the library. It doesn't call Lite anymore. But TF-Lite converter from a saved model, you pass the address to where's the model. Then you define the types of optimization that you want this basically algorithm to do. For example, you can say, I want to optimize for size and just say convert. It's a predefined algorithm. It basically goes through these layers, basically quantize those based on what you expect, and it will return you this TF-Lite. This is the quantized version of the model. You save this. This is still a frozen graph. You save this, and you load that in the whichever environment that you are basically deploying it to. Now, well, of course, this is just a simple scenario of it because there are a couple of things that you need to change. One of the challenges, at least I personally experienced with that, when you build custom models, the quantizations most of the time are not, they don't exist in TensorFlow or other libraries because those libraries also like a public open source. So if you build some custom model, custom types of layers, they might not be able to quantize it for you. So you might need to build it actually yourself. Okay, so for most of the types of layers that you use, they have already something, but for certain layers, they didn't have. Like when I was working, for example, they didn't support LSTM for the quantization for certain reason. I don't know why. Anyway, so the next types of quantization becomes quantized-aware training. Now, the idea here is that in post-training quantization, you simply have a model and you keep cutting it, binning the values. In quantized-aware training, while you are training the model, you teach the model, you kind of like make the model aware of that it's going to be quantized in the future. How can you do that? By mimicking the quantization in a forward pass. So during the forward pass, you quantize, basically clip the weight values. During the backward, you use the original weights to update. So the model learns during the forward, every time I want to make a prediction, my weights are clipped, right? So you use that knowledge in order basically to train the model. That becomes quantized over basically training. So it's kind of like a, look like this. If this is your original model, you basically add this quantization nodes, fake quantization, so for weight and for activation. And this only works during the forward pass. During the backward pass, they don't exist. So they don't do anything basically. Okay, so that becomes the quantized aware basically model. And in order to do that, for example, if you're building this sequential, for example, TensorFlow model, you basically, when you build the model, you pass the model to this function, and then you train the model basically. So this, what it does, it basically requires you to have introduced certain layers as quantized. So where do we introduce the layers? This is where you introduce. So you basically import that function, quantize annotate layer. And for any layer that you want to mimic the quantization, when you build the neural network, you just put that layer inside this function. When you build the layer convolution 2, I just put it in this function, and that's it. So that tells the model for the training that this layer need to be, for the forward pass, to be quantized, basically. And during the backward pass, it doesn't do anything. All right. And this is just an example. If you have a custom layer and you want to quantize it, basically, you need to apply some basically changes to it. But yeah, so that's the quantization. This is just a couple of examples of post-training quantization versus normal versus quantized error accuracy. So for mobile net, if the original model, the large model, for example, is 70% accuracy, post-training drop the accuracy, quantized error much higher, right? So quantized error you see is always, this one doesn't have, much higher than post-training quantization. So if you're planning targeting quantization, maybe when you build it, just do quantized error because it doesn't do anything. It technically you're just adding a couple of import basically functions. And this is the latency. Look how faster is the quantized error even in compared to post-training quantized model, or in compared to basically the original model. So it has a really huge impact, especially if you have a larger model. Even if you deploy a larger model on the cloud, you know, the reality is that we quantize those. Because if I have the same model that can give me, I can quantize it, becomes half faster, basically, or twice faster, right, or 3 times faster, why I should serve that one on the cloud? I just serve this one. So you still do the quantization. It's a good practice for building a neural network that quantize as you go. You know, just, yes.
Why is it faster than post-training quantized?
Because so what you do in post-training is that you basically quantize the nodes based on some fixed values that you have. So we say that I want this float, I want this weights to be all float 32. It's fixed. During the quantized error, you basically let the model know that, hey, whenever you want to do this, it's going to be clipped. So when you train, maybe you basically come up with a better parameters, better, I don't know, like basically weights that helps you to achieve the goal that you have. So it's technically should be faster also because you let the model choose on those quantization, those float values that it thinks is better. So you let the model decide on those rather than you fixing those.
Yeah, but like at the end of the day, like both of them are going to be quantized to the same numerical precision, right? I say it's like
No. So in quantized aware, let's go here. So in quantized aware, basically we did not specify that fixed quantization. In post-training quantized, you fix it. You say that float 32, float 16, certain layers, which kind of like, here, no, it doesn't necessarily need to be fixed. Your model could have an option to basically apply different quantization, right? If you fix, you can also probably fix it. You know, I don't know how the import work for it, but probably it has the option that you fix everything to the same quantization. But from the model perspective, well, I think the model comes up with a better presentation of itself for quantized aware in compared to post-training quantization. Because from the perspective of, if you think about it, yes, they kind of do the same thing, but in one scenario, you do it after the work is done. In the other scenario, you do it while you're training. So the model probably learns a better, basically, set of weights, set of parameters. Maybe I don't need to go through this branch. I set it all to 0. I go to a different branch. So it ends up being a better, more optimized model. In the other one, you just quantize them at the end, right? So that's a great question, thanks. And then from the size perspective, it's just much smaller, this types of model, basically, compared to the original model. So, all right. Now, the next thing we're going to talk about is going to be pruning. So pruning is, so quantization was one way of reducing the size of these models. And the other one is pruning. And the pruning, the idea is, again, similar to what you saw in random forest idea. But here is that, well, I have this model and I'm going to get rid of certain connections, right? Because they don't do anything. And if I have that connection, I technically, my model need to still go through those, do this computation, so it makes it slower. Whereas if it doesn't make anything, so I just drop it, you know, I just set the weights to 0, so like don't do anything. So that's the idea of pruning. The overall idea, I don't know if you heard of this or not, but we'd rather, basically we'd rather to have sparse model in neural networks than dense model. Denser models normally is like overfitting and then they're much larger, versus sparse model. So pruning is one of those techniques that increases the sparsity of the models, right? Because you basically set a series of nodes and connection to zeros. You create this more like a sparser model. They become more efficient. Now, this is just an example of before pruning and after pruning. So there's this concept called lottery ticket hypothesis. So if you think about I have this model, that's this model, and I prune it, basically I reach to this one, right? So if you think about neural networks, when you want to build a neural network, the first thing you do is random initialization, correct? Every time, you randomly initialize the weights and stuff like that. And then let's say after you prune the model and everything you trained and pruned, you reach to this. Do you agree that there is a subset in your random initialization that could have randomly initialized this? There's a chance that you could randomly initialize this parameters, this weights, this structure. That's called lottery ticket. So there is a chance, because if you think about it, we searched through all this space to come up with these weights. And with weights at first are random. So there is a chance, that's called this lottery ticket, and that's the probability of it, that you could have initialized that. You know, you could have basically reached to that value. So, and that basically, that also means that, well, we know we can reach to something like that. You know, it's kind of, we know it's possible to achieve something like that. So, again, also pruning is something that basically is evolving as we basically go through. It's kind of like it's an active research area. There are a couple of ways that we do pruning. A simple scenario could be based on the magnitude. So if you have these weights, basically, you apply some sort of like a magnitude, basically comparison among weights, and basically you prune those. Or like simple scenario, if you think about like you pick a neighborhood of nodes and you pick the maximum weights and put the rest to 0. You say that, okay, it's like what we do in convolution, basically, something like that. I think Keras does that itself when you, because Keras has a pruning, we will see that also. I think what it does is based on magnitudes, if I'm not wrong. But so when you do this pruning, there's this hyperparameter which is called sparsity. So you define a sparsity and you say that start pruning, and it basically prunes gradually, not all of a sudden, until you reach to this sparsity, keeping this level of accuracy or of one score that I want. So basically it starts gradually prune and basically looks at the impact that pruning had, and it continues basically. So that's the idea. So this is just an example of the if you want to do this pruning with Keras. So TF mode, basically you import that TensorFlow model optimization, sparsity, polynomial decay, and you basically say what's the initial sparsity you want, what's the final sparsity you're looking for, and then basically what's the total steps that you want. You let this to go through a schedule. So it basically goes through nodes, cut the nodes, basically gets the feedback and continues this loop. And this could be an example of what you see for sparsity. So for example, inception, general one has 78%, and it still gets almost same sparsity, same score, but look at the percentage of sparsity. So you reduce this model almost half, and you still have the same accuracy. These are large models, like from the perspective, if you think about it. And basically, MobileNet, you go also to half, right? So most of the time, when you deal with neural networks, like for example here, these are like 90% pruning, right? Most of the time in this type of neural network, large models, there are lots of like predictions, they don't do anything technically. And in order to basically improve it, make it faster, we do certain basically types of techniques like pruning, quantizations, and stuff like that, make these models smaller. It's still same types of models, same knowledge, but there are certain fields they don't, or lots of basic connections that they don't do anything. You get rid of those. Any question on that? All right, so we'll stop on this. Then we have lab. So what we want to do today, we start with basically our labs on GCP series around basically deployment and stuff like that for the models. So for the first part, we want to, how many of you have worked with GCP before? Is there anyone that hasn't worked with GCP? Okay. So the labs that we're going to go over, we're going to just quickly review the GCP for those of you that haven't worked with GCP. And then we're going to work on basically the concept of like a bucket. And then we go over Cloud Run, Cloud Functions. And the idea will be that what if I have, what if I have some data that I'm basically extracting, maybe API calls or something, and I want to write this data, so this is my data, I want to write it to a bucket on GCP, and it's like a sporadically, or like a once in a while, basically I keep writing, or maybe every moment I'm basically writing data. And then I want to have a function that listens to this bucket. And anytime this function basically listens and it says that, well, there's a new data. Because there's a new data, this function says that I'm going to run certain types of codes. So there's someone that listens to a bucket based on the activity will trigger something else that does the job. And this something else maybe writes the data here or writes to another bucket. And this loop basically could continue, right? So that becomes the idea of what we want to talk about. Now, before that, so let's just start with just quickly. So first time when you start with your GCP, you basically have something like this. Then you start here, basically you go to here, you say new project. You just basically create a project. If you have an organization, if you use your NUI Northeastern account, you normally will see organization Northeastern. But otherwise, you basically just say create. After you create, this page comes up. Okay. So the first thing about GCP is that for the project, project ID is not your project name most of the time. So here, if you click on this top on your project, you will see name and you see ID. So when you want to connect, you need the ID, not the project name. Okay, so just keep that in mind. Now, when you work with GCP, there on the left, basically left bar, you normally have a. Let me connect with my other machine. This. All right, so on the left, basically, you will have something like this, list of all the products that's available on GCP that you can use. A couple of those that are going to be really important for you is going to be this IAM and admin. It's basically, that's a place where you, I think we did have before lab on when we build a service account to make connections. So in here, basically in IAM and admin, you can go to service account and you can basically build a service account. Like, for example, I have service account that service account, when you download it to your local machine, it can authenticate your machine in order to make a communication with your project. Right? So that becomes, for example, one way of doing that. Then you also have this other stuff, which we have cloud storage buckets, which we also saw that in the previous lab. So you have buckets that you basically have some bucket like this. So let's say I have this bucket, GCP bucket, and I want to, so you build a bucket. Let's say you build a bucket and you send data to this bucket. Now you have this goal that every time this bucket, basically I want to listen to this bucket. I want to have a function that always is actively listening to this bucket. So when you are on this page, the bucket, go to other services. So you go to here, other services, and you see these options, export data to PubSub and process the data. So export data to PubSub. So PubSub is the idea of publisher subscriber. That's the PubSub basically means. So the if you go first time, because it says that it needs this data flow API is not enabled, so you need to hit enable first time. But think about the idea of PubSub as, so you basically create two things, like as a publisher, there's a subscriber. Publisher, it's publisher or a topic, actually, topic. So you're building an app and your app receives different types of data. Let's say one of the data that you are receiving is you crowdsourcing data from Twitter. One of your groups here was doing, I don't know which one. And so the publisher or topic could be Twitter. All right? So you basically can build something called a publisher or a topic, and you call it a Twitter, basically. It's a Twitter, basically. Now, let's just enable. So then what this topic means that anytime there is a data, okay, and that data relates to this topic, okay, so I have a data in the bucket, from the same bucket over there that you saw. And because this data is related to this topic, I basically send a message to this topic, hey, you have a new data. Okay. So that topic is the publisher, right? Publisher has subscriber. What are subscribers? Subscriber are services that basically listen to that publisher and they are ready to see if it has a new data or not. So publisher basically has data and there are subscriber that they actually, this way, they're listening to this publisher. Says, hey, you have a new data for me? Yes, I will run some code or I will trigger some services and stuff like that. So normally this is what you do in like a pops up idea. You have a topic, and if you have different types of data, you end up with different topics. Every topic is focused on one thing. And then for that topic, you build different subscribers, basically. It doesn't need to be one subscriber because you could do different things with that job. So, well, this is pretty slow. Now this is working. Okay, so now here basically says that the job name is, this is defining some job. But before we go to this, so let's first look at the publisher concept. So if you go here, you go pops up. Okay. This is real-time messaging. So now I have already this topics, but let's say for you don't have a topic at first, and then you basically all you need to do is I say create a topic. You can give it basically a name or something. Your topic basically you have these options. Use a schema. You can force certain schema for the data that comes to this topic. For example, you can enable ingestion. You can enable message retention. That means there's a certain period I will keep a message. If no one subscribe, pick it up, I get rid of it, and stuff like that. And then basically you just say create. Okay, so basically you create a topic. After that, after you have a topic, if I go back here, so let's say I pick a topic. Now I have a topic. Now inside the topic, you see on here it says subscription. That's where basically you can create subscription or listener to that topic. So you can basically say that I want to create a subscriber, and you define that subscriber and a name, like let's say test. And then you say, what is the topic you want this subscriber to listen to? And then what is the types of delivery that you want to do? So basically, if you hover over this, it tells you that if it's pull, subscriber must request a delivery. That means the publisher doesn't tell to the subscriber. Subscriber need to call and pull the data. Says, hey, you have a data, right? For other types of the basically deliver message as soon as they are published. That means the publisher, the other services will call to the subscriber, hey, I have something ready. So you need to think about your application, what is making more sense for you to always listen and get, or whenever it's ready to basically receive it. Then, so you define basically this, for example. Then you define some retention policies and like how long you want to keep the message. Acknowledgement deadline, that means the subscriber has maybe 10 seconds basically to acknowledge that, hey, I received this message. Kind of like some sort of like acknowledgement. You can add some filter. You can basically, these are like different things that you can basically add. And you basically can say that we'll put some retry policy. If it didn't work, you want to retry quickly, or do you want to retry with exponential backup? Exponential backup for retry, especially if you work with APIs, if you make so many calls, you can easily get blocked sometimes. So what you can do is define exponential backup time. That means first time you make a call and you get blocked and you try 5 seconds after. If you still get blocked, then exponentially the number changes. It gets to the point that maybe adds 2 minutes gaps because you keep getting API blocked, right? So that's the idea of exponential block. So you basically create something like that and so Now, I have this basically subscriber, okay? Now, you can create a snapshot if you want to reprobe. You can purge a message, delete it. Those are like different things that you can do to the with this snapshot. Now, if we go back to what we were doing, so here on the bucket, the one option that you had was that, well, I want to connect to the pub sub, this bucket, and you can do that via data flow job. Okay, so you basically select, you have the bucket name, you choose the region, and then you say that I want this cloud storage text to be sent. The cloud storage is saved as a text. I wanted to send it to pub sub as a basically batched message, you know? So this is what you're doing. And here, so cloud storage input bucket, which is the pub sub that you're targeting to send it to. For example, I will say that I'm sending it to this one. This is the topic, and that we create a subscriber in that topic. Okay. And so basically you can define some temporary location. Then so I don't know what's enabled data flow prime. I don't know what does that do. So if this is for your data lineage, remember we talked about it, so to know where the data goes and stuff like that. Then here you can basically define if you want to add additional workers, because you also, I wanted to have multiple workers because lots of data comes. So I want to batch them, and lots of workers send the messages to the pub sub rather than sequentially. Maybe you can define the number of workers. You need a service account, like which is the service account corresponding to this project, to this account that you're using. You select that, and then you do run job. So what it does basically, was at one time, which one we're missing? No. Just select. So now we have this data flow job, basically, which is responsible for listening to that bucket. You can trigger it manually. So this is basically what's going to happen. So if data comes to here, this basically reads the data, writes it to the pub sub. Okay, so right now, expanded, 0 of 2 stage succeed. So two things is running in the background. There are two things basically it has. So we will see what's going to happen. So this will, if it's successful, reads the data, send it to the pub sub. At first, it's also, they have this problem with cold start also. It takes time maybe to come up. But then you have this information on execution time, job metric. You have some cost analysis, how much is costing for you overall, something like this. It gives you some estimation over that. And if there's some recommendation insight based on your pipeline, it also has that. So any question on that so far? All right. So that's one way. And again, you can basically go, we're not focusing on data flow much, but just play around with the workbench and then like a pipeline. It's kind of like the overall process is straightforward. So this is actually, I think, initiating, it's not running, but. Okay, so we will let this run for now. Now, the other one was process data via cloud run function. Okay, so now cloud run functions, so these are kind of like ephemeral basically types of functions that you can create that only exist when there is a trigger. After the trigger, they basically shut down themselves. So just they come up, they do the job, they basically go there, right? So from those perspective, these cloud runs are really good types of function because they are like, you don't pay for them like Kubernetes, compute engine, we will see those later. You pay a fixed cost of keeping them up. Okay, like you have a Kubernetes server, it's going to run, you pay for that cost, even if there's no request. On the other end, the cloud run basically, if there's no request, there's nothing. When there's a request, it basically comes up, right? So that's the difference. But, well, it's the usage are also, there are differences. Like a Kubernetes, maybe you use for something like you're serving. Here, you're probably not using a cloud run for serving a model because if there's nothing running and there's a user request, user need to wait for you to spin up a model and stuff like that. So for different tasks that you might use the cloud run. But anyway, so you basically give it a function, decide on the region, and then you have this trigger type, and you say that, well, how do you want this cloud function that you have to be triggered? Via what types of basically messaging? So here is on cloud storage. That means it will listen to this bucket, basically. You could have it based on HTTP. So that means when you say is HTTP, that means you basically make an HTTP request to spin up this. So think about the scenario where you could use that. You could do pops up. So Cloud Run could also listen to the same pops up, basically. Like they don't need to work, they're not together, they're separate. It could be a different approach. But you have a pops up that your Cloud Run also will listen to that pops up. And when there is a basically new message that being pushed by or received by the subscriber, this basically will run. So that pops up. It could be listening on Firestore. Firestore, remember, is like a memory storage, like types of memory data that you read, quick reading, like a cache memory. That could be something. So like when you read something to a Firestore or memory store where it's fast read, then it will trigger another function, for example. And it could be other triggers, basically. And if you go other triggers, it technically gives you for almost everything on GCP. So if you work on your project and you don't know if you can basically use it as a trigger to bring up a service for you, just go other function and you have a list of everything that you can automate with the Cloud Run, right? If you find it over here, then you should be fine. Also, it has this like a third party still, for example, gives you an option here. So far, I think it's just a Datadog. I don't know. So does that make sense so far? All right, so let's go back here. So then let's go to bucket. So we will say that we are listening to this bucket. This event type is going to be, so what types of basically event you want to listen on this bucket? If something was added, something was deleted, something is like a finalized, metadata update. So you decide what types of event should be the trigger. So we just say that finalized. Then which bucket we are listening to? Let's say, for example, we say this one. Do you want it to retry on failure? Yes or no? And then if you go to more options, basically, where did it go? I had more options and it doesn't have anything anyway. So then it comes to the part below, which is a runtime and build and stuff like that. Now, here is where you put your code. You want this cloud function, Cloud Run, to come up, but what do you want it to do? The code that you want it to run is going to be this part. And it basically supports almost all languages that you can write for. So, for example, if you do Python, you basically go to Python, you select your Python version, then, so you can upload zip file. You can basically, your code also could be in a cloud bucket. You can just say that zip from a cloud storage, or you can basically just put inline editor, inline code, depending on what you want to do. But what you want to keep in mind here is that there is this first requirement.txt that you need to have. But the other thing is that this function, this code that you write, it needs to do certain things. Okay, so it's not just plain Python code. For example, because here we want to listen to a bucket, it gives you a default code. So you understand how your function should be listening to a bucket. So you need to start by importing these function frameworks. And you have this code that you decorated with that. Function frameworks cloud event. Okay, so this is like a type. And then you have this function. This function will receive a cloud event. What's an event? When something was added to the bucket, for example, that's an event. So it will receive that event, which is a protobuf, for example, gets the data out of it, gets some information out of it. But this, like, how should I know which information I get out of it? Is a protobuf. Just maybe get one and then just go. Or if you search probably on Google, you can find the list of fields that it has. You extract what you want and you do whatever you want in this code. And if you want it, after it's done, to write it to a bucket, you basically add the code here, right? So you can have series of function here, but what is important here to remember this one, entry point, okay? Entry point that means among the codes that you're adding here, think about the concept like in Python when you do main, that's the main. Which code is the main one that this trigger will run and that will run the rest? So you need one code as entry code, and that name should be there. Okay, don't forget that. So your entry code name should be there. That code could trigger everything and run the rest of the code that you have. So, so that's this one, and then here. I was like, there's some other fields missing. So that one, the runtime build and security settings. So here is where you define how much compute do you need for this task that you're doing. So like how much runtime memory do you need? You need to have a sense of like a tested beforehand to know that this code that I have, how much memory it needs to run on basically like a worst case scenario or basically best case scenario. So have some idea, find a range, and then basically decide on that. How much CPU do you need? This is like a fraction on CPU. What's a timeout? Basically, you define concurrency. How many requests you want this to run max, like a concurrent. So if you are doing lots of processes, like you receive thousands requests, you need to put that over there because you don't want, if you just put one, it becomes this queue of an infinite queue, the never finish technique, right? So you want to be sure that if, depending on your application, if you have lots of calls, lots of data, then you need to have this high number because you need to be sure you can concurrently do all the tasks. If you don't do that and you get lots of calls, it's going to be a queue and it never ends. You know, that scenario, your cloud runs forever, right? Because there's a queue, it's keep running. So maybe that's not a good practice for cloud run. Maybe you need to use a VM or Kubernetes or something. So this kind of like also comes to the auto scaling, how to scale. Basically, you say that a minimum number of instances, 0 means if there's nothing, put 0, right? You could maybe for a certain task, certain application, you're like, I always want one cloud run to be always running. I don't want to have 0. For like maybe for something happen, I always want to have 1. So you put this 1. And then you define also on the maximum scaling. That scaling means that how many new cloud run can start in order to be able to feed to your request. You can also have that number, but you need to think about the cost that they will have. In reality, when you build those, you need to keep in mind that when you put a larger scaling with concurrency and stuff like that will increase the cost overall. So you need to find a balance for that. Then you default like what's the service account that you're using for this basically app or basically this cloud run. Then you also have this runtime environments. So think about you have a code and in your code you have this variation like environmental variables like that you want to load those. Like I don't know, name of the bucket or like some keys or something. Technically you shouldn't put the keys over there because you're in the same project, you actually don't need the keys. But let's say, I don't know, from GCP, you make a call to somewhere else and you need a key for it. And the worst case scenario is that you put the key in the environment. And best case scenario is that you actually put the key in something called secret manager on GCP and you read from there, so no one can see that code. But anyway, so you basically add those variables that you have here, list them, and it's kind of like a key values. Bucket name, this is the value. I don't know, like project name, this is the value, and so on. And then you basically say deploy function, and let's see, we don't need that. And this will basically deploy something to the Cloud Run. So now, if I download this, okay. So if I go back first to this this data flow job, so basically this one told me that there was a this two is finished. There was a pops up message that's sent. So basically it did write, and then basically I don't know, it's just a short name pops up that writer. Now let's look at the. Oh, there's also table view. Oh, okay, yeah. So that's the easier one to read. Now, what I want to do is that, so we have also now this subscriber. So where's the subscriber? We can look at the log. Zero. So what I'm going to do is that I'm going to upload the file to the bucket. Okay, so just, where is it? So file was uploaded to the bucket. Happen. I go to Cloud Run. So that's a function. What's the time now? Here, 20:38:38. And then let's go here. So we're going to go back on this later, but so there's a job and there's a service. Service is the one that we just defined. It's kind of like as a service comes up. Requires authentication. Maybe I should have removed the required authentication. If it's coming through. Let's see what's going on. We did add a file, and there's a one running job here on the data flow, but I don't see it here. Yeah, one job is running, but for some reason I cannot see where is the actual. Okay, now this one is also running. Sometimes it takes time for them to come up. So, this basically tells us the, request count. There is there's this request. Let's see if we can see the log now. Still the same. Let's see.
I think that log shows that that was triggered whenever the main file was uploaded. So it's not an old log.
It should.
It says file name main.
Did you see that?
Yeah.
Oh, I didn't.
You know, the,
Where?
fourth last line, file colon and main. When we read the final log creating an.
Oh, yeah, okay. Yeah, sorry. All right. So it's already there. I'm waiting for that to show up. Okay. So this, it was triggered technically, but we don't do anything with the code. So that's why we didn't see anything. Now, so does that make sense, the process? So basically use the bucket and triggers two types of things. One of them is could be a pops up, and the other one could be basically your data flow. So this is the data flow one. And then what data flow did, basically, it has this running job. Basically, it sends a publisher to a publisher, and publisher has a subscriber, and basically this loop continues. The other one was that to just use the Cloud Run, and the Cloud Run basically listens to the bucket. Okay. Now, what we want to do, we want to pick this same thing, but this time using some actual code. And we have this lab on Cloud Run, which basically, so we have this code. We have this app code, which it does what it does. It creates like a fast API or Flask API. And there's a main road of that API, which if you go on it, this says hello from this lab. Okay. Then we basically add two new functions. One function is called upload file. When you go to that function, basically, when you go to that address, okay, what it does, it basically uploads something, right, to the bucket, just like as a test. So imagine part of your API is user can go there and they can upload their files. And when they upload the file goes to the bucket, right? So because the file goes to the bucket, so then it should trigger something also, right? The other one is there's an address on your API is called query. If you go to the query address, what it does, it basically, you have this database that you query against it. It writes a query and returns the query on the page to the user. Okay, so that becomes, here, example, we search against BigQuery, basically. Okay, so, and then we serve that basically on this port IP. So what we are doing here, we have that code, and we basically create a Docker file, basically Docker image with that code. And what we want to do is that we want to deploy this Docker image to here. So basically, there's something called artifact registry. Oh, sorry, let me zoom in. So artifact registry is a place that you can basically create an artifact or store your artifacts. First time you go here, if you don't have, there's nothing here. So you basically say create repository. When you say create repository, you need to choose a name for the repository, and then you need to define what types of information, code or something is in that repository. Is the Docker base, Maven, NPM, Python, and so forth. So your repository is not a mixed combination, it's going to be separate. So if you do a Docker, for example, you come up with a name and you decide a region for it, and the rest of it's, at least for the default project, and you do just hit create. you basically create a bucket. Or basically registry for your buckets, your data. So then if you go to that here inside the bucket that your artifact registry that you created, there is an option here on top says setup instruction. Basically, it tells you on your machine, if you want to connect to this bucket and to write Docker to it, you need to run this, right? So even if you, let's say you're doing a CI/CD as part of your Git action, and you want to, every time there's a delivery deployment, you want to deploy it here. So you put this basic, or some sort of, basically assuming that you have some sort of authentication with between GitHub and GCP, you basically write this, run this, so this authenticate that basically Git action that you have with bucket, and then it writes the Docker image, the new Docker image here. All right, so that becomes the process. So now, yeah, so we do that. So inside the README, we have put the, oh, this is so small, sorry. We basically put the steps for you. So basically, steps to follow. First, create a folder on your machine, put this code in it. And then basically, this is the requirement file that you need. Create this Docker file. Then what you want to do is that you want to push your Docker to that address. So here, so this basically what I'm doing here is that I do Docker build, tagging it, and it's going to go to this address, and that's the bucket that, so on GCR.io, so this is assuming that you have already ran this. Okay, so if I go back here, or if we do assume, we don't assume that. So first time, you basically run that, and it basically says that, well, you're authenticated now with that bucket. So then you do a Docker build because you already have the Docker file in the folder. After you do the Docker file, and then you basically want to do Docker push. So you basically, it says, is writing the, basically pushing the latest Docker image that you have now to that artifact registry. So if you go back here, GCR.io, this is just now basically created over here. So now if you go down here, the next step that you have, you want to deploy that. Okay, so that means you wanted a Cloud Run to, you wanted to Cloud Run to basically deploy this new Docker file that you have on that Cloud Run. Okay, so you can, a couple of ways that you can do that. Now, the easiest scenario is always to just using the basically platform like directly. So if you go back here, actually, I think if I'm not wrong, inside the inside the artifact registry, if you are doing a manual deployment, if you go on the image, select the latest, on top, deploy to Cloud Run, deploy to basically GKE, Kubernetes, deploy to Compute Engine, VM. So it also allows you to directly do that. So if you wanted to do it from here, you basically, if I say this, it basically brings this up, which is technically a same page if I do it via Cloud Run. So if you go to Cloud Run on the other end, and here I say deploy a container on top, and it says that you want it to be deployed as a job, or you want it to be as a service, okay? So job basically is execute the code, finish, done, job. Service is like when you listen and basically you're just kind of like a service that you basically keep going. So for example, I see as a job and says that, okay, where is the address to the image? So it shows already your artifact registry. So basically you go here and says that, well, it was this one. It was this one, is the latest one. And give it some names, choose a region, number of tasks, basically. This is how many jobs basically runs in this container. Then you go to this container information. So this is where you basically going to define the settings for that code to run. Okay, so it's including if there is any basically command, if you want it for that container, if there's any argument, like you have certain codes that have a command to run, certain arguments to run. Then you define the resources that you need. If you wanted to have a health check, that means there's some sort of like address that you can check if it's healthy or not. You basically can add that here. Then you can go here again. This is within for the container on the tab, under the tab container. You can go to variable and secrets. If you need series of variables or secrets for this container to run, you add those here. Volume mount, that means if there is some bucket that you want to mount it to this, like be sure that is being used for that, you can mount it here, or volume like not a bucket, maybe just a rented, basically a space. Okay, so that becomes something. Then you can go here to volume. Here you can also add the volume. You can go to connections. So now the connection part is, I have this project and I want this project to only work maybe internally. No external IP, no external connections. Then you basically, this is where you need to define those information. There's something that we will talk about next class. This concept is a VPC, virtual, basically private, kind of like a connection. It's kind of like, it's a virtual network, private network technically, right? So when you build projects and you want these components within that project on GCP to be able to communicate with each other, but also you don't want external person, anyone to access to that. So you build this virtual network, define certain IP and ranges with that, within that network, and you put your component services on that network. By doing so, it's like you have this private network that it doesn't have any accessibility by outside. Okay, so, and then you basically add this connection. Then if there's a security, basically you can, normally I leave that for Google managed encryption key, just let the Google to do that. So you do all of this, and then here basically on the bottom basically is that, well, task capacity, timeout, number of retries per failure, run as many tasks concurrently as possible. This is, if you have lots of calls, just let it run parallel, just finish it for you. Otherwise, you need to define how many parallel job you want to use. But think about from the job perspective, what Cloud Run does for every job, it spins up another node in order to quickly finish all of it, basically. Okay, so when you want to work with something like this, if you have lots of job, that could easily cost a couple of $1,000s a day. Okay, because just it spins up lots of server, basically jobs for per call that you have. So if you have something like that, which you need lots of concurrent jobs, maybe Cloud Run is not a correct strategy, because the cost of all of this becomes a lot, right? If you need something quick, you want it to be quickly done, maybe you need to do Cloud Run. But if doesn't matter if it's quickly done and you don't care about queuing or something, then maybe it's cheaper for you to have a Kubernetes or VM that you pay a fixed price per month. It slowly goes through the data instead of keep spinning up another node and another node, the cost that Cloud Run has. So just those are things to keep in mind when it comes to something like this. So then you basically say create. So this, as you see on the other side, also technically it was the same thing. You say that I want to deploy artifact registry. It could be deployed from GitHub. So this is for those of you that you want to connect it to your GitHub. Could be just using inline function. So just that means the code part. And the rest of it is basically the same thing, okay? Both scenario. So here when you say create and basically, well, let me just do it on this one because the code actually is part of this Docker. So central, let's put this US East one. So here asks you for authentication. Basically, this tells you this is the endpoint. This address, this whatever that I'm deploying is going to be available on this address. Okay. Now it asks you, do you want to allow unauthenticated people to access that address or they need authentication? For now, I've just set it unauthenticated, just as a lab to experience, but definitely that shouldn't be like that for you. So then basically you have this billing, basically it says that how do you want to pay for this? Do you want it to be a request based, per request you pay, or do you want it to be an instance based, like a fixed cost per instance? So you need to figure out this cost to come whenever you're trying to build it, have some like a table to know that, okay, this is a per instance, this is per API call. What if I make this much call? How much I'm going to pay? Like you get some sense which one is better for you. So, and then for ingress, for the traffic that comes, do you want it to be internal? If it's a private network or all? I don't have a private network right now. I just say, just let it for all of those. And so this is the container port, the port that you are also using within the Docker to expose for your fast API or Flask, if there is any command or something. And then you just say, also on the bottom, I didn't go away, but there's a SQL connection. You can also connect it to a SQL to read data from, basically. So it's running, it's normally take a minute or two to actually spin up, to come up. But let's go to the logs. Maybe it actually is already running. So you see, failed, log one service started, deleted service. This is the URL address. So if we go on this URL address, what we get, hello from the intermediate lab on top. So this is the API that within the Docker is right now exposed. Now, if you go on top and you basically say that upload, because remember, if I do upload, what it does, uploads a file to a bucket for us, right? So I did not define if you go to, so there are a couple of things we didn't define. So I needed to define that, what is it called? This environmental variable. What's the bucket name? Which bucket do you want this to run to? So if I go here and do an edit, variables and secret, add a variable. Let's see, what do we call it in this, in the Docker? Bucket name. And then let's see what's the bucket name that we have. So let's pick a bucket and just say deploy again. And then one thing also you can see while this is coming up, manage traffic. So if you have multiple cloud runs, you don't need to only run the last one. You can actually, let's say you have multiple versions. You want to test the traffic like a canary deployment. So you can say manage traffic, and I can say that, well, I want the first one and the second one, and I want the second one to get, I don't know, like 80% of the traffic. So the first one becomes 20%. And then you monitor it and maybe you gradually basically increase that. So now if I go back to this, and then file uploaded to GCP bucket. So if I go to the bucket now, and I do enter, fresh. Yeah, the first file you see 9156. So that's the file that was just uploaded. Then maybe you also have this. Remember there was a query, for example. If I do a query, what it does in the background, it actually search against a big query, extracted data, and return the data that extracted from the databases. So these all become the that Cloud Run basically that we have. And the last thing about that Cloud Run is that, so we just connected this Cloud Run to the Docker code that we have, but you might actually want this to be triggered based on something. So right now this is manual. What if I want this Cloud Run to be triggered? So here you go on triggers. You go to triggers and you say, I'm going to add a trigger for this Cloud Run. And what you can basically decide what's the trigger. I want it if there is a cloud storage trigger, pops up trigger, fire store, other event triggers. So now if I go to other event trigger, basically triggers, and I can say if artifact registry, if I wanted to run, if there was a new Docker file basically we added. Right? So you can basically say that what's event type, Docker, let's see, Docker, deleted, finished upload, yeah, could be. This is basically asking me that, hey, you don't have this rule, and you say that, okay, enable it. So you enable that rule, and then you basically define if there's any, that's the default. You leave that. Service pass the same and just say save trigger. Now, what will happen here is that this will be triggered anytime you have a new Docker file uploaded to your basically artifact registry. And then that will run, and that run basically spins up something for you, and then you basically continue from there. So it's kind of, you just connect this loop yourself, like how you want things to trigger each other on your lab, on your project. So what you want to do is that definitely go on GCP Labs, try to do 2 of these labs. So you need to finish this Cloud Run Labs and Cloud Function Labs. So Cloud Function was previously, like I think as of this year, Google removed it. So we had Cloud Function and Cloud Run. Now they kind of combined them together into one thing, but still you can do the labs. So definitely do these labs, get some sense of like how you can